Welcome back, everyone. We are working on homework 2.5. Homework 2.5, question number 6. And in particular, it is part D we're going to be focusing on today. Now, if you recall from part it's A and C, we're driving through town and we have a velocity, an initial velocity of 16 meters per second. And then a car pulls out in front of us some distance up, and we slow down at a certain rate. That is a deceleration rate. Our acceleration is our deceleration rate of negative 3.2 meters per second squared. Or I should say the other way around. Our deceleration rate of 3.2 meters per second squared is the same thing as a negative acceleration rate, but I'm sure you probably already knew that. And of course, our stop, our intent is to come to a complete stop, and so our final velocity is 0 meters per second. And one other thing that we're told in part D here is that the car is at a distance of 55 meters from us. Now the question is, how much time can we afford to waste? So that is, what is our reaction time before we slam on the brakes? We found out in part A that our braking time, that is, I'll put our TB, time for braking, is 5 seconds. We were told that. But the reaction time is the amount of time where you're not braking, you're processing what's going on. Of course, all of our brains need some sort of reaction time, and we might call that the delay time. And so to illustrate this maybe a little more clearly, I'd like to draw a small graph here. So this is going to be a velocity versus time graph. And our initial velocity is going to be 16 meters per second, and we intend to slow down to a stop at 0 meters per second right here. But the first part of our moving along on our time frame, on our timeline, is going to be our reaction time. You react, or you think about it first, and then you react and slam on the brakes. So our reaction time is going to be the amount of time where we're doing nothing. We have a constant velocity. Our acceleration or deceleration rate is going to be 0 meters per second squared. And then we're going to slam on the brakes and hopefully stop in just the nick of time so we avoid hitting the car in front of us. So that we know that our TB, or our braking time, is 5 seconds. That's going to be this right here. But what we want to find is our reaction time. That's this right here. You know, I should probably write that TR or TRT, time RT, right in there. Now you might say, well, we'll just find how long it takes to decelerate from 16 meters per second to 0, and that's an amount of time, subtract 5, and we're going to have our reaction time. But it's not quite that simple, because we don't have a constant deceleration rate in the distance that's in front of us, the 55 meters, because part of that 55 meters is going to be us reacting, or that is really not reacting, or just the reaction time. It's us processing what's going on. So part of that 55 meters is going to be spent not decelerating at all, and the other 55 meters is going to be decelerating just enough. And by the way, this is negative 3.2 meters per second squared, decelerating just enough to stop hitting the car in front of us. So we do not have a constant deceleration rate. So what we're going to do is we're going to take our displacement right here. And I know this is the time scale, but just think of this as the total distance between us and the car in front of us as being equal to 55 meters. And so we can use what we know about our deceleration to find our delta x. I'll call that delta x1, and we're going to find a delta x2 by subtracting the 1 from 55 meters. If that's a little confusing, let's just start by finding our displacement for the deceleration part. This second part right here. This is going to be part. Oops, that's going to be part 1, and the other one is going to be part 2. So that's 1, and this is going to be segment 2. So we're going to find 2 different displacements. Let's see. I'm going to start up here at the top. So for part 1, our deceleration. Well, our velocity, initial velocity is 16 meters per second. Our final velocity is going to be 0 meters per second. Our acceleration is negative 3.2 meters per second squared. The amount of time that we come to a stop is going to be 5 seconds, and we want to find, you know what, to save some space, I'm going to move these guys. I'm going to move these guys up top, or up next to them. So I'm breaking my rule of writing all of our givens in vertical lines, but oh well. A is negative 3.2 meters per second squared, and our time is going to be 5 seconds. So what is our displacement for section 1? Well, we have an equation for that, and if you recall from our 5 equations of motion, this is going to be equation number 4. That's where our displacement is going to be equal to the initial velocity times time plus 1/2 times a, or acceleration, times time squared. So in scenario 1 right here, or that is the actual braking part of it, our displacement, I'll call it displacement 1, is going to be 16 meters per second times 5 seconds, right, because that's our time, plus 1/2 times the acceleration of negative 3.2 meters per second squared, times our time, squeeze that in there, 5 seconds, the quantity squared. If we punch that all in and calculate it out, we're going to get a delta x, or a displacement 1, of 40 meters. So if we go back over here, that means that our displacement total is going to be displacement 1 plus displacement 2, which really means that our displacement 2 is going to be our displacement total, and you probably already figured out where I'm going with this, minus displacement 1. It's just the difference between 40 and 55 meters, and our displacement 2, I lost my train of thought here. Here we go. Our displacement 2, sorry, is 15 meters. So now let's use this little section down here and our knowledge that our displacement for part 2 is 15 meters to solve for our time for part 2. So really it's our reaction time. It's really this right here that we want to find. So let's use what we know to solve for our time for part 2. So now let's write down our knowns for part 2. Our delta x2 is 15 meters. Our initial velocity is 16 meters per second. And if you remember, we're not decelerating here. We're staying at the same acceleration because this is our reaction time. This is our processing or our delay time. So that means our final velocity is going to be 16 meters per second as well. Not only that, that means that our acceleration is 0 meters per second squared, right? Because we're not slowing down or speeding up. We're maintaining our acceleration. And so we want to solve, for our time 2. If we look and see what we have, we can solve for our time 2 by using equation number 3 of motion. And that is displacement is equal to 1/2 times VI plus VT, VF, I mean, it's an F, times our time. Well, if we solve for time, delta T is going to equal, let's bring our 2 in the denominator up to the numerator on the other side. So 2 times delta x over vi plus vf. I'm really running out of space here. Delta t is going to be 2 times 15 meters over 16 meters per second plus 16 meters per second. If we calculate that out, that means that our delta t2, or our reaction time, is going to be 0.94 seconds. So the reaction time delta t2, call it 0.94 seconds.